Today we're mainly looking at polynomials. We're going to do two examples. They're both polynomial examples. But we've got the three types. And so we will see applications of all three types of questions that we can do. So polynomial, rational, and square root. Okay, so over the next couple of days, that's what you got to figure out is make sure how you do it. It's pretty straightforward for the most part. Sometimes interpreting what's going on can be a little wonky. We'll see that in example 2 in particular. The first one's pretty straightforward. The second one's a little bit stranger to think about what's happening, make sense of it. And as often happens with applications, the numbers are not always as friendly. So that can cause some issues sometimes. Otherwise, this is almost identical to what we've been doing over the last several days. Just using the difference quotient to find instantaneous rates of change. Let's take a look at this example. The movement of a certain glacier can be given by this function, d at t, where d is the distance in meters that a stake on the glacier has moved. So that's just pinpointing one particular position on the glacier because glaciers are big. So talking about glacier movement would... I guess it makes more sense to talk about which part of the glacier, especially since you can think about it might be turning as it's moving around, that kind of thing. So the distance that a stake on the glacier has moved relative to some fixed position after t days. Find the rate at which the glacier is moving after 20 days. So remember when we introduced this unit, we talked about average rates of change for a day, and then the problem is we forget about that and we get going with this instantaneous rates of change, which is kind of the important part of this unit, but it doesn't mean average rates of change aren't relevant and aren't important and aren't useful for other things. So, and I said, remember where instantaneous rate of change comes from, that it comes from average and that slope formula. And think about, continue to sort of think about what each of them are, how they're different, how they're the same, when you might use one or the other. So for example, if I just found, let's go ahead and we got to find this anyway, so let's do it. Let's find d at 20. So 0.01 times 20 squared plus 0.5 times 20. So it looks like 4 plus 10, so 14. So it's traveled 14, that stake on the glacier has traveled 14 meters in 20 days. And if we wanted, we could turn that into a rate. 14 divided by 20 would be 0.7 meters per day. That's the average rate of change that the glacier has moved over those 20 days. That might be something that you want to know. I don't know. Might be relevant, might be important, depends on what you're studying this for, doing this for. So that is still something you could do. You could find average rates of change by looking at a particular point. That point was like from 0 to 20. Was the average that we calculated there. But you could pick any 2 points, 10 to 20 obviously, 5 to 10. I mean, you could pick any different points and sort of see how the average rate of change, I suppose, compare it on different intervals along the way. But we're supposed to find the rate of change at which the glacier is moving on the 20th day, after 20 days. So that's an instantaneous rate of change. So to do that, we're going to use the instantaneous rate of change formula. Yes?
So this isn't just like a straight line? It's not like it's accelerating.
Right. Well, it's quadratic. So it definitely isn't.
Oh, yeah.
But no, good point. Because you would think that if it's just kind of flowing in water or whatever it's doing, it would be a relatively consistent speed. And if it was, then it would just be the slope of the line. But again, it's a stake. So if the glacier is turning, the whole glacier might be traveling at some kind of consistent speed, but that stake isn't. Or who knows? Or, I mean, water flow changes and it's melting and there's wind and, lots of things going on. So the instantaneous rate of change equals the limit as, we're talking about t here, so I'm going to say t approaches a of d at t minus d at a. You could also, sometimes you might start with the formula with like f at x and f at a. That would be a thing as well because it's just a formula, and then sub in your values, but I'm going to start with the variables given in the question. And we're doing this for 20 days, so it's the limit as the number of days t approaches 20. Okay, and I think you know what to do, so go ahead. So I got this far. What do we do next?
Could you do synthetic division, or you could use the quadratic formula?
Okay, so this is interesting because it's funny how, like, this is something you probably have noticed that you're good at and you're understanding, you're feeling good about, and then all of a sudden we do an application and you get to this step and you're like, wait, what do we do next? Like, a lot of people, I think, have those moments and say, I thought I knew how to do this. This one looks different. And it can be as much as having a decimal in there can change things. So I like the idea of the quadratic formula because often with quadratics, we use the quadratic formula when we have decimals. Why? Because factoring with decimals doesn't usually work. But essentially, we want to factor this. That's still what we want to do. Why do I want to factor it? What has to happen? Again, if you ever get stuck, you want to know from this step, you want to have absolute certainty something has to happen here for this process to work. What is it that has to happen? We got to get a t minus 20 factor. So normally with polynomials, we'd factor, but like I said, this one doesn't look factorable. The quadratic formula may not actually help because it finds the solutions, the answers. You'd have to turn those back into the factors if you did that. You could, but I think there's a better way.
Do you do synthetic division?
So you could do synthetic division. Why do you say that?
Because you already have the factor.
Right, so we know that t minus 20 wants to come out of this. So I can start with that, and I would absolutely recommend you doing that. I don't even think you need to do synthetic division to tell you the truth, but you absolutely could. That would work. Because I can just say t times something is going to give me the first term, so this is going to be 0.01t. And 20 times something is going to give me 14. So how do I do that? 14 divided by 20, right? And that'll give me what I need here, which is 0.7, so plus 0.7. However you choose to do it, make sure that you understand that there's different ways of doing it. Factoring it might not be possible, though, because of the, or as easy and straightforward, at least because of the decimals. And you certainly need to figure this out. You can't just leave it blank. It's going to be relevant for the answer. But the cheating trick here is we know that t minus 20 is going to work. Can anybody think of something else you could have done that might have worked in some cases? It might work.
Maybe like get rid of like decimals.
Yeah, and somebody this morning said multiply by 100. That's a bit tricky. You'd have to multiply by 100 over 100. You could. So you'd have 100 t minus 20 on the bottom. Or if you factored this out and turned it into a simple trinomial, that'll kind of work. It looks like this, 0.01 t squared plus 50t minus 1400. Still not the easiest thing to factor. It works out to negative 20 and positive 70. So it's totally up to you what you would choose. So you'd get 0.1 t minus 20 t plus 70. You can see how those are kind of, this line and this line are the same. Okay, but however you choose to do it, you just got to make sure that you can do it when the numbers are not quite as friendly. So that's where I want this written out once more, and then sub in. And this works out to 0.9. And then again, this is where in applications, in this case, I don't think it's too bad, but in some applications, it can be a little bit tricky thinking about what that is. Because up till now, when you got that answer, it was you just left it. You're done. It said find the slope of the tangent, you found the slope of the tangent. But we have to do therefore statement to answer the question. So what is the 0.9?
It's the instantaneous rate of change at 20 days.
Yeah, and what do you know what the units are? Like I would go back up and read the question and figure out what the units are.
Meters per day.
Meters per day. And remember we calculated the average rate of change over that entire course. And what was it, 0.7? Meters per day average. So right now it's going faster than the average. Because the average includes all the different speeds it traveled at, that stake on the thing, throughout those 20 days. Good. Therefore, it is going 0.9 meters per day after 20 days. Good enough? Okay, one more. The profit in dollars of a manufacturer selling digital phones. It seems strange, doesn't it? Digital phones. It's not really what you call them, I guess, but they are. Is given by the function p at x. Oh, and this is supposed to be 30,000, not 3,000. Where x is the number of phones sold. A, find the average rate of change from 100 phones to 150 phones. All right, so let's do that. Yeah.
What does 102x mean?
X equals 100 to X equals 150.
Oh.
Is that what you mean?
Yeah. Okay.
So this is going to be just the slope formula, the average between these 2 points. So it's going to be P at 150 minus P at 100 over 150 minus 100. So what do we need in order to do this? Well, we need those two values. So go ahead and find those when you're ready. So I got those two values.
Oh,
I've double checked them, so I think they're right. So it might just be a negative or something in there. If you got something different. Now I'd like to stop here though and think about this. Can anybody interpret these numbers?
how much bigger they get?
So,
Like the profit
okay.
on 100 phones sold and 150 phones sold.
So for 100 phones sold, what would you say?
I mean, $10,000.
Well, not quite.
Lost.
They lost. It's negative, right? So they're losing money.
And are they BlackBerry?
Yeah, very good. Possibly. I'm going to do a little sketch of this so that we can continue to make some sense of it. Oh, and when you look at the function, it's quadratic. It's opening downwards, and this is the y. This is the vertical intercept, right? The p-intercept or the y-intercept. Negative 30,000. So it starts down here somewhere. And it's going to go up and come back down. And we can see that at 100 phones, they've lost a lot of money. Well, at 0, they started down 30,000. And that makes sense. They had to spend $30,000 to open the plant. Like they had to spend money to get the operation up and running, I suppose. Buy the material, that kind of thing. Okay, so they started way in the hole. But now they're only at 10,000. And then by 150, they're getting closer to 0, breaking even. So presumably, they're going to break even, but eventually they're going to max the if it continues to follow the quadratic relationship, they're going to max out their profits and they're going to start losing money again. Now, in the real world, you have an interval where the model works, and then after that interval, it stops working. Just like throwing a ball. Throwing a ball follows a quadratic relation until the ball hits the ground. Right? And then it's no longer quadratic. It's something else. So that's true of almost everything. It's only between certain values. So after it maxes out, why would it start losing money? I don't know. We're not going to worry about that just now. We're just going to answer the questions and not worry if it's all the way realistic or not. But it looks to me like they started losing a lot of money. By 100 phones, they've still lost a lot, but they're doing better. After selling 50 more phones, they're overall making money, so they're on the right track. So let's go ahead and finish answering this.
Wait,
So this works out to,
haven't they lost more money after they sold more phones?
no, this is for 100, this is for 150. So this is their profit after selling 100. This is their profit at 0. This is their profit, overall profit at 100, and this is their overall profit at 150. So they're less in the hole, so they've made money. And it works out to 187.50. Now what's that? 187.50.
Because of phone.
Sort of. How do you figure this out? In the last example, it was meters in seconds, so it was meters per or meters per day, actually, right? So what would this one be? If this is P for profit, and this is number of P phones,
Maybe how much they gained or lost per phone?
say that again?
How much money they gained or lost from each one?
From each phone, per phone. This is the profit per phone. See, this is what I mean. It's a little strange. So this is the average rate of change between 100 and 150 phones. They profited 187.50 per phone. The total amount of profit they earned is more than that. But the average per phone was 187.50. So this is profit per phone.
So if you wanted to, like, say they only sold like 150 phones or something, or only sold like from 100 to 150 phones, could you find out like their overall profit over like the time period by like finding the area under the curtains, like seeing if they made more in the
Yeah.
like do you like if the space under the positive part of the graph is larger than like the space underneath the or above the negative part of the graph?
But wouldn't it boil down to just what position on the graph they're at? Their total profit, is it positive or negative?
Oh, yeah. Okay.
But no, but what you're saying is you're on the right track, and that's where this, not in this unit, not in this course, but that's where this math does go. You start looking at the kind of stuff you're talking about. It's tricky when you're thinking about profits. These ones are, at least I find a lot of people find that these ones are tricky. Okay, so that was A. B is the instantaneous rate of change for the 3000th phone. Phone number 3000, find the instantaneous rate of change at that point. So again, we need P at 3000 in order to do this. And it works out to 120,000. What is that?
Oh, wow.
Yeah.
Bank.
How much they gained out of this 3,000?
Yeah, that's their profit. That's their total profit. That's what their profit is at. So now they've gotten themselves out of the hole. They no longer are in debt. They've made money. They've made $120,000. Good for them. And that sort of goes along with the way that I've sketched this out, where they did eventually cross the x-axis and get out of the hole. Okay, go ahead and solve this one. So if we get to this step, this is where some people might get stuck, but if you remember, we have to get an x minus 3000 factor, and then it's just up to you to figure out what goes in the bracket. So I got negative 0.05x plus 50. 150,000 divided by negative 3,000 is 100
How'd you get the
is
first one?
50. How do I get the first number? Well, I just think about how this times this has to give me that,
Oh,
right? This coefficient is basically always going to be the same as that. Not necessarily always, but basically, I think, right? Is that good? And you can always check this by doing a full expansion. I think this would be a good idea. So x times 50 plus negative 0.05x times negative 3,000. Make sure that gives you 200x. If it doesn't, then you've made some kind of a mistake up to this step. Because if it doesn't give you 200, then x minus 3,000 isn't a factor. But if you do a check just for the middle term, like you've got these two terms from the first and third. So if you just check the middle term and it gives you 200x, you know you've got it. And this works out to negative 100. That's what I got too. Somebody interpret that.
That's like their, that's how much they're in debt at 3,000.
Not how much they're in debt at that point. Remember, at 3,000 phones, when we subbed it in and calculated, their profit equals 120,000. Adam?
You're starting to like waste money now. They're on the downwards.
Yeah, so they're actually at this part somewhere of the curve. The slope of the tangent is negative, and in other words, they're losing money on every phone they sell. Stop making phones. Close the plant. You're done. You're losing money. I have no idea why that would happen. We were thinking about this morning. Somebody said, what if you like saturated the market, and so now the phones aren't selling for as much? So it's actually costing you more to make the phone than it is. Yeah, that's not a bad idea. It's possible that your plant, your factory is designed to make a certain amount of phones, and making more phones, you have to pay overtime or buy more product. Like, I don't know. That's not really how this would work. You'd have to invest more money to make another amount of phones. What would really happen there is your profits would go down, but they would start going back up again. Like, so, I don't know. Again, like I said, it doesn't always, these questions don't always fit with how we would expect the real world to happen, but that's okay. But the interpretation is kind of interesting. Therefore, they are losing $100 per phone at 3,000 sold. Your interpretation of these questions is important. You have to interpret the negative or the positive. Is it increasing or decreasing? Like, you have to say that. Don't say, therefore, the profits per phone is negative 100. You will lose a mark for that, right? You have to make sense of it. Even if it's a little bit tricky, what does it represent? What does it mean? What's happening in the situation? And that's why, and you know, for the test, you only have to do it for your final answer, but I think it's important as you're working to think about what each of these values means. What does this value actually represent? What does it mean? What did the average mean? What does that actually mean or represent in the real world? Okay, I think that can help you with your final interpretation of your final answer.